Good afternoon, ladies and gentlemen. Welcome to the pod reveal presentation of Delft Hyperloop. Today we will discuss to you what we have gone through the past year. And we will of course unveil to you our brand new vehicle, ATLAS02. But before we dive into all this, I want to take you on a journey of the future of transportation. So where do you see yourself in 10 years? This is a question that many of us are confronted with on various occasions throughout our lives, especially at this point in our early engineering career. And the truth is, we don't know. We don't know what life will be like 10 years from now. And to illustrate this point, I would like to take you back 10 years. Many of us team members were still in our last year of primary school then. We did not know with what kind of friends we would spend the years to come, and we did not know what kind of topics would spark our interest. We did not know that we would be studying engineering at Delft University of Technology, and we did not in the least bit expect that we would be working on such a cool project. On a personal level, I am sure that everyone has gone through their own changes. Some bigger, some smaller. But if we look at society on a social level, I think we can all agree that we went to quite some things together. And since we're in Delft, let's focus on the technological side of things. We can see that in the past 10 years, the focus has been on the development of smart technology. 10 years ago, almost no one owned a smartphone. And I'm pretty sure that nearly every one of you has one in their pockets right now. Since 10 years, we can see that WhatsApp and Instagram, for instance, have made their introduction, and Facebook and Twitter have gained popularity in our lives. And if we look at these developments closely, we can see that they all have one common denominator: to increase connectivity. We're always available. We're always available for a phone call or for a text message. We always want to know where our peers are and what they are doing. And this increase in digital connectedness has also led to an increase in demand of physical connectedness. We are supposed to be able to be anywhere at any given moment. And this in turn resulted in extremely high pressures on the infrastructure as we know it right now. Roads are becoming more and more congested. Trains during peak hours as busy as they get. If you decide to go somewhere by plane, you have to wait hours and hours before you can board your flight, which sometimes even takes longer than the flight itself. As engineers, we have the privilege to look at the future like we want it to develop that technology that we want to live with in the future. So let's talk about the future of transportation. What do we want? I say we want something comfortable, we want something fast, we want something easy. Of course, I'm talking about the Hyperloop. My name is Rinneke van Noort, and I will talk you through what our vision of the future of transportation is. The Hyperloop is a new form of transportation that relies on pressurized capsules with passengers or cargo that travel through tubes. And these tubes can be pumped down so that there's hardly any air inside. This reduces the aerodynamic drag, thus reducing the amount of energy needed that the pod needs to propel itself. The Hyperloop makes use of a passive electrodynamic suspension system. It levitates using magnets. This reduces the friction between the pod and the track, even further reducing the amount of energy needed to get from one point to another. In total, we can see that the Hyperloop can reach speeds of over 1,000 kilometers per hour, while only using very limited amounts of energy. So let me take you on a journey to what we envision the future to be like 20 years from now, and we'll slowly count back to where we are right now. 20 years from now, the system will be finished, and it will not only be relevant for us engineers anymore, but for you as well, the future Hyperloop passenger. So what you encounter is, for instance, the station interior. And you can see that it quite resembles a train station, with a lot of light colors, a lot of space. And this is because we make use of the same system, a turn-up-and-go system. This means that you can just go to the station and board whichever Hyperloop you choose. The exterior of the station can also quite be compared to a train station. You can see that it is very light. It blends in to urban spaces, but the large difference is that we don't need to have tracks on the surface. Hyperloops in urban areas will travel underground, and this way they do not take up significant urban space at ground level. As being safe is one thing, but feeling safe is at least equally important. Our engineers pay great care to the experience and feeling safe in this vehicle. You can see that we make use of a lot of light colors and natural materials to make sure that the experience is as comfortable as the ride itself. Actually, our engineers have been working so that you can actually experience this Hyperloop system by yourself. They've been working on a VR system that will allow you to act as if you're traveling with a Hyperloop. And for the very first time today, we will show to you this VR experience. So I would like to invite Igor, one of our partners, on stage to test the system out. Is it working? Are they switched on?
Yeah. No, it's okay.
It should be. You can see that indeed the whole station resembles quite that of a train station. The Hyperloop tubes, even though they travel in a vacuum, they enter airlocks before they enter the station, which means that you can just safely see whatever is happening around you. You will not have to buy tickets in advance. You can just do that whenever you arrive at the station. And this means that you can leave whenever you like. The Hyperloop stations have been designed in such a way that it is optimal for the passenger and designed intuitively so that you will know exactly where to go without having annoying things in your face that tell you where to go. The inside of the Hyperloop has, like I said, been designed to feel as comfortable as possible. And you can see the sky panel that mimics the light of day of your destination. This creates an open feel and a more natural feeling to your trip. The screens on the side can be used for whatever you like. You can use it to look up information of your destination or to share photos or videos with your peers. The door design is comparable to that of an airplane, as they pretty much travel in the same environment. All right, so let's get back to the presentation. Thank you, Igor. No? So how did you like the interior and the experience?
It's extremely awesome. I'd like to experience personally
All right.
in the nearest future. Thank you.
Thank you. If you think that this VR experience looked nice, feel free to try it out after the presentation. We will have it set up in the foyer that you can enjoy during your drink. We also have displayed our passenger pod there that shows our vision of the future Hyperloop. So 20 years from now, we will have a network in Europe, a network connecting 48 big cities. And this way, we can replace 2/3 of European flights between these cities. We aim to reduce, therefore, the amount of energy that is needed to get from one point to another within Europe. And as we are expecting hundreds of millions of passengers, this network will allow us to actually reach the 2050 climate goals. The challenges we're facing while building such a network can actually be seen on the map. For instance, if you want to go from London to Paris or from Stockholm to Helsinki, you will have to cross over 185 kilometers of waterways. Furthermore, you can see that especially Western Europe is quite densely populated. This means that we will have to alter between going above ground and going below ground whenever we are building it. Maybe not as relevant in Europe as it is in the rest of the world are the various climate conditions that we will have to work with. You can think about hurricanes, tornadoes, but also earthquakes and volcanic eruptions that could disturb the Hyperloop system. And these all have to be taken into account while designing such a network. To get here 20 years from now, 10 years from now, we will have to have the first link. And we do not know yet whether that indeed is from Amsterdam to Paris in under 30 minutes, or somewhere completely different, for instance in Asia or the Middle East. While building this first link, we see that we come across three major challenges. The first challenge is the financing of this link. Infrastructure projects always cost quite a lot of money, and we need not only governments to invest, but also private parties of various countries. And this enables us to create unique collaboration between these various parties. The second major challenge we can see is the standardization between the countries. For instance, when you travel by train from the Netherlands to Belgium, you might encounter that you will have to change the design of your train according to the track that you find abroad. As with the Hyperloop, you are experiencing these borders multiple times per hour. You do not want to stop every time, since one of the main advantages is getting from one point to another in only a very short amount of time. And this brings us at the third challenge, maybe the least straightforward challenge. And this is high-speed switches. And with high-speed switches, I mean the ability of Hyperloop pods to exit and enter the Hyperloop highway. You want to get from Amsterdam to Paris and not stop in Brussels, but you also want to get from Brussels to Paris. And so far, research has proven no feasible conclusion yet to how we should approach these high-speed switches. However, we see that with the increased popularity in Hyperloop technology, that we are sure that some solution will be found in the near future. To get here 10 years from now, 5 years from now, we will have to have the first high-speed test track. And this high-speed test track is extremely important, as we need to guarantee safety for passengers and cargo that are traveling in these Hyperloop pods. We also need to be able to test out different types of Hyperloop systems, to test out all the various options that we think are feasible, to make sure that in the end we can have one Hyperloop system that works for every situation. And one of the key factors in creating this high-speed test track is to get politics and the government on board. And in fact, we are already cooperating with various government parties. As of today, we have actually published a report we wrote in collaboration with the government. And this becomes more and more important every day. This is why Delft Hyperloop has launched Hyperloop Connected. Hyperloopconnected.com is a website where basically everyone can share their research and share their findings on the Hyperloop topic. We can see that it is being used by us, students, but also by companies. And it's made to create that one Hyperloop system, that every specialist can work on their specialist topic while still having one point where all the information is gathered. But it's not only for researchers, it's for anyone interested in the topic of Hyperloop. So if you want to know more, please feel encouraged to take a look at hyperloopconnected.com. And this is what brings us to where we are today, the 3rd of June, 2019, where we will be revealing our brand new prototype. But before we dive into the specifications and the stories behind this vehicle, I would like to give you some background information as to why we're building this vehicle in the first place. And this story started in 2013, when Elon Musk wrote an alpha paper about the Hyperloop. He did some calculating, he did some thinking, and this is also when it really sparked the interest of other people as well. But then he realized that this was a unique piece of engineering, and this piece of engineering could not anymore be built by the engineers who had been doing the same thing for decades already. This engineering required a brand new approach. We required the engineers of the future to build the technology of tomorrow today. And so he launched the SpaceX Hyperloop Pod Competition. And this is the reason that we're building this vehicle. The SpaceX Hyperloop Pod Competition is challenging student teams from the best universities in the world to come up with a design that could be used in future Hyperloop technologies. And the conditions that we're racing in are pretty straightforward. We have a 1 kilometer long steel tube that stretches out in front of SpaceX headquarters in Los Angeles, California. Inside this tube, we can find an aluminum I-beam. You can use this beam to either guide your vehicle or not use it at all. The only rule is that we're not allowed to damage it or alter it in any way. The most remarkable feature of this tube are the 2 doors that you can find on either end. These doors can hermetically seal the tube, allowing SpaceX to pump down all the air. And this results in near vacuum conditions. And what the implications of these conditions are for our vehicle, Arjan and Elia will talk to you about that later. The challenge for us lies in the time frame that we have to do it. We have 1 year to design, build, and test this vehicle. At the end of this 1 year, we will travel to SpaceX, and we have 1 week to prove to the SpaceX engineers that our vehicle is indeed safe and reliable and does what it is supposed to do. We have to pass 122 tests before we can actually make that final run. Of the 22 teams competing in this competition, only 3 will make it to that final run, and they will get 1 chance. 1 chance to go as fast as possible and beat the Hyperloop speed record of 467 kilometers per hour. But life at Delft Hyperloop is far more than just this 1 parameter. It is having your good days, having your bad days. And we would like to give you a feel of what life is like at Delft Hyperloop. And for this, I would like to invite on stage project manager Arjan Buijsert.
Thank you, Rineke. And indeed, we cannot capture this competition by just talking about top speed. We cannot just capture this competition by talking about this 1 parameter, because there's far more. The challenge that Elon Musk created is remarkable, and there's nothing comparable to the SpaceX Hyperloop Pod Competition. But to understand this remarkableness and to understand why it's so difficult to compete in this competition, we need to zoom in. We need to have a closer look at those run conditions that Rineke talked about. And if we do so, we can again find those 3 major challenges. First of all, our pod will need to operate in a near vacuum environment. And this is mostly an issue for electronics. As soon as we arrive at the competition day, our pod will be entered in the competition tube and the doors at both far ends will be closed. And this will be the signal for the SpaceX officials to start the pumps and to decrease the pressure inside the tube. And then issues arise for electronics on board on the pod. Our CPUs, the board computers, and the motors might heat up faster, or the batteries can swell due to the reduced pressure. Or we could have sparks in between our high voltage components. So to make sure that all our electronics will survive this near vacuum environment, we need to pay great care to all electronics during the design phase. We added many safety features and performed extensive testing to make sure that the pod will operate as it should. The second conditional challenge we find here at this competition is track misalignment. As we just learned, there's an I-beam within that tube. And upon first inspection, the I-beam might seem perfectly straight. But if we take a closer look, we find that it's not. The I-beam segments have not been perfectly aligned, introducing bends and bumps. And our pod will need to cope with them. And at low speeds, this is all fine. But at high speeds, we will still encounter these bumps. At our top speed, our wheels will rotate at hundreds of rotations per second, hitting these bumps, introducing major loads. And this is a complex problem, and we have several engineers dedicated to developing new wheels that will survive this run, and that will survive these track misalignments. The third major conditional challenge from this competition is the tube length. And even though the competition tube stretches the entire street in front of the SpaceX headquarters in Los Angeles, it's just 1 kilometer long. And within that 1 kilometer, we will need to set our top speed. In this kilometer, we will need to prove that we have built the very best Hyperloop prototype. And to do so, there's actually just one relevant parameter: power to weight. And power to weight can be described as the ratio between the amount of power a vehicle has on board and the own mass of the vehicle. Whereas conventional vehicles, such as cars, often reach their top speed after several kilometers, we cannot do this because we are limited by the tube length of a kilometer. And there's just one thing that we should do to reach the highest speed possible: accelerate as fast as we can. And this is determined by our power to weight performance. So what we needed to do was build a small and compact vehicle that remains lightweight, but that's still packed with power to reach that power to weight performance. So these are the three major conditional run challenges: the near vacuum environment, the track misalignments, and the tube length. But these are the challenges that we face by competing at this competition. But we are not just participating. We want to win the SpaceX Hyperloop Pod Competition. And by doing so, we decided to push the boundaries of engineering. We are engineering for the edge, and we are engineering for that very limit. And that introduced all kinds of new challenges. And a perfect example of such a self-inflicted challenge is our braking performance. Because at the end of that tube, we will need to brake and not hit that steel door at the end. So this is our pod speed profile. And we could determine that we need to brake faster. We could optimize our braking system. However, doing so would come at a cost, because all those braking forces would also be introduced in our other components. And we would have to reanalyze the entire design of our vehicle, make sure that all parts will survive these major loads. However, we decided to do so, and that also gained us benefits, because by shortening our braking distance, we can accelerate longer and thus reach a higher top speed. And doing all of this in 1 year is a major challenge. Overcoming all of this, I would say, is nearly impossible in 1 year. Yet, the challenges that we talked about so far are just purely technological. And yes, we are here in Delft, and we like to talk about technology. Of course, it's called Delft University of Technology in the end. But these challenges just scratch the surface. They're the tip of the iceberg, and they do not cover the entire story. And furthermore, all of these challenges are the challenges we foresaw at the beginning of the year. We based our deadlines around it, we determined our planning, we made the team structure around these challenges. However, you could also have foreseen them. Even though you're not a part of the team, you could have known that we would be facing these challenges. And this afternoon, I would like to tell you some of the things that we did not foresee, the unpredicted, because those things are the things that greatly shape our learning and our experience. We started the year with 40 team members. And within this team, we share a lot of similarities. We're all approximately the same age. Most of us live in or around Delft. Most of us have finished their bachelor's, and of course, we're in here with one clear goal, winning that competition. But if we take a closer look, we can also find our differences, and some of them are easy to overcome. For example, we all have different body lengths. But well, we can deal with that. With some flexibility in how we cooperate, we overcame this challenge. And we all have our own different habits and our own ways and styles of working. But that's fine. We got used to that after several weeks. But we also have 11 different educational backgrounds in our team. And that's a good thing, because we have specialists that can work on the subsystems of our pod. We have someone who is good at working at each of those subsystems. However, it's also like we're speaking a different language. We all have our own our own set of skills that meet our studies, and sometimes that does cause some difficulties. For example, this is Detmer. He's the lead of our navigation and control department, and I still recall the first meeting I had with him. I went down to his workplace and we worked to talk about planning. But instead of replying my questions, Detmer started talking in 3-letter abbreviations. I'm working on the EMS, the FSM, the IMU, and I had no clue what Detmer was talking about. I didn't understand his language. So that meeting, we did not talk about planning. We talked about the way we work, and we learned how to communicate together. And even though we have differences within the team, we're all still located here in Delft, the Netherlands. So we are working according to approximately the same rhythm. We are enjoying the same holidays. But as a high-tech engineering team, we are working together with companies from all around the world. And we find different cultures at other places. For example, we are working together with a Chinese company that manufactures our battery cells. And one of the major holidays in Chinese culture is Chinese New Year. And when we started this year, we had no clue that this event would shape our own planning, would shape our internal deadlines. But as soon as we figured that China is on a lockdown for a few weeks during Chinese New Year, we had to shift quickly. Because the powertrain engineers had to design the batteries, test the cells, and order them before Chinese New Year would start. But there's more in the story. Because this story is not only about the surprise by those different deadlines we find due to cultures around the world, it's also one of the first instances where we were surprised by the difference between theory and reality. We had been designing our battery system around a specific cell that we found on the internet that would outperform all other cells. And then we started testing, and we found a cell that was even better. It outperformed our original design. So not only had we to be flexible with respect to that deadline on the other side of the world, the powertrain engineers also had to be flexible with respect to their own deadlines. And within a few days, before Chinese New Year would start, they had to redo the entire design of the battery system and order the cells in time. And you can imagine, this was a major deadline for our powertrain department. But every department is working on their own parts of the pod, and every department has its own structure and its own deadlines, and therefore its own challenges. And we face many challenges in this team, and some of them are easy to overcome. For example, just by reading the manual. And here we can see Joppe. He's one of our software engineers, and he is known in the team to be a profound reader of manuals. And actually, you'd be surprised by how often this has already fixed our issues. But as we are working on something new, we are doing things that have never been done before. And in that case, there's no manual that you can read. There's no book to read, and there's no studies that could have prepared you for the challenges to come. One of those examples is this, because we are reinventing the wheel. As I mentioned, our wheels will rotate at hundreds of rotations per second when we are reaching our top speed. And while doing so, they will hit the bumps that are caused by the track misalignments. And this is a major, complex dynamic problem that's almost impossible to calculate or to model in a computer. So what we do here, we get our theory as good as possible. We make the best design we can come up with, and then start testing. And in these cases, it's not about reading the manual, it's about making your own. And overcoming these challenges is not only about the result itself, it's about learning, it's about discovering, and it's about finding our own strengths and our own weaknesses. At the beginning of the year, we knew that one day we would enter the production phase. And as we have a totally customly designed vehicle, we knew that many of our parts would have to be produced by ourselves. We cannot go over to the store and buy our suspension mechanism. It just does not exist. So we need to make it ourselves. But also, at the beginning of the year, most of our team members had never touched a machine before. We didn't know who would be good at turning, we didn't know who would be good at milling, and we had no clue whose talent lies at what machine. But what we did know is that we would have to make all these parts by ourselves. And at the beginning of our production phase, mistakes were made. And we have a whole collection of failed parts in our office. But that's fine. In the end, we're all doing this for the first time, and we need to learn by trial and error. We need to learn how to do this. But after several weeks, we still had barely any parts that were approved during our quality control. And time was running out, as our assembly deadline was already approaching. So we sat down with the entire production crew and we had a meeting. And we discussed, how can we solve this? How can we make sure that we finish our parts in time? And we determined who was good at operating what specific machine. We determined who was good at making what specific part. And we matched our strengths with our challenges. But these failed parts were not only caused by our own mistakes. We also had some bad luck. Upon inspection, we found a caliper, which is a measurement device, that had a deviation of 0.2 millimeter. And this might not sound as much. In the end, it's only the thickness of a sheet of paper. But for our purposes, this is not good enough. For many other applications, a deviation of 0.2 millimeter will be fine. You can just use the part and everything will work as it should. But in our case, a deviation of 0.2 millimeter might lead to the part failing at high speeds, or might lead to entire assemblies not fitting together anymore. So we had to stick to our own quality criteria, and we redid all of those parts that deviated by the thickness of a sheet of paper. But in the end, our production crew learned how to do it. They learned how to operate the machines, to deliver parts that meet our strict quality criteria. And I think that here we can find one of the core aspects of Hyperloop life, one of those core elements of our story, and that's learning, becoming a really good engineer. An engineer that's not only equipped with the theory from its books or the theory from lectures, but an engineer that has successfully been through the entire product lifecycle, that has designed parts and realized them, parts that work together in one complete machine. And a few of our team members worked on a nice little side project visualizing this learning experience. And they illustrated the tremendous effort it takes to make just one of our parts. And this cool video that I'm going to show you is not made from our perspective, but it's made from the perspective of a part. And I think this is such a cool video. And it is so nice to see what all that dedication has brought us throughout the past few months. But the team's dedication is not only shown in pod engineering, it's also shown in daily life. Because as soon as Delft Hyperloop started, a lot of ordinary things all of a sudden became extraordinary. The team takes up all our time, so a lot of daily life struggles are changed. For example, at the end of the day, we often do not go home, but we stay at the office and we make dinner together in this small kitchen unit, so we can continue working throughout the night. And as you can imagine, by the size of the kitchen, this is quite a challenge, preparing food for so many people. So in the meantime, I think we can say we have also become experts on takeaway food here in Delft. But there are many more things in daily life that all of a sudden become a challenge. For example, when to go grocery shopping, because as soon as we leave the office, all shops have been closed already. Or during lunch, we often have discussions when to do the laundry, because no one has time to do that. And the creativity of our team members is also not only shown in the pod, it's also shown in the few breaks we have. And a few of our team members got creative with an old flight case, and they built a ping pong table out of it, to empty their heads in those little moments we have in between solving those challenges. And we're not only pushing the limits of engineering, we're also pushing the limits of ourselves. And I think if there's one thing we have learned by now, well, that's that fatigue hits everyone. This is me after approximately an hour of sleep. The day before, we had been working, and the night before we had been working on preparing our pod for the test that would follow the day after. So, at 7 in the morning, we went home for an hour of sleep and got back and started testing. And at this moment, I'm trying to coordinate that test. And we all needed some coffee throughout the day, but in the end, we managed to continue, and we pulled off a successful test. And I think that this is also one of the core aspects of our team, because we always kept on going. And I could fill an entire presentation with these kind of photos. Photos of people being tired, photos of people giving it all. This photo is taken around Christmas time, and Christmas is a hectic time in Delft Hyperloop. We are working on writing a detailed report on all our design decisions. We are finishing the 3D models, and to make sure that we finish all of that in time, we were working throughout the day, throughout the night. And it took its toll, and Lucy took a short power nap on the couch in her coffee corner. And even though I could share different photos with you, and I could share all those different stories, the outcome would always be the same. We kept on going. Delft Hyperloop has been a huge roller coaster. We have been high up, as you can see here. After weeks of preparations and weeks of work, we finally got our motor spinning. And you can imagine the relief. And we were cheering and we were celebrating the victory. And you can see Roland finally hearing the sound of the motors. But as Delft Hyperloop is a roller coaster, we have not only been high up, we have also been deep down. And these moments follow up at insane speeds. In between these two photos, there's approximately 15 minutes. Because after we got our motor spinning, we continued testing, and we continued testing with more intense tests. And by doing so, one of our motor controllers exploded. And as you can imagine, that was a major setback, and sometimes that's difficult to cope with, especially in these kinds of situations. Because if you take a close look outside of the window, you can see that the sun was already rising, and we had to deal with it. And throughout the past few months, each department has been working on its own challenges. Each department has had its own focus points. But in the end, we're still one team working on that one pod. And even though we are sometimes working on something else, there are special moments within this team. And what you see happening is truly amazing. It's remarkable. This photo is taken right during a wheel test. But on this photo, there are not only suspension engineers, there are not only testing engineers, there are people from all around the team. Everyone stopped working for a few minutes and came together to celebrate this special moment. So throughout the past months, I think I can say we have become friends. And maybe I can even say that we have become one big family. And we always kept on going. We kept on going. And not to earn any money, not to earn study credits, or because someone forced us to do this. But we did this to build something completely new. And we did this to build something that we believe in. And after months of hard work and months of dedication, it's a joy to be finally able to share with you what we have been working on. And it's an honor to introduce you to the newest prototype of Delft Hyperloop. And this is ATLAS02.
Ladies and gentlemen, on behalf of Delft Hyperloop, we would like to reveal to you our new Hyperloop pod, ATLAS02. On July 21st, this vehicle will compete against world-class prototypes built by student teams from the best universities in the world. The pod is built for only one goal: to reach the highest speed possible. This will be accomplished by combining the power-dense drivetrain system that propels the vehicle and the fail-safe braking system that brings the pod to a standstill. The suspension system will guarantee a silky smooth ride, while the health of the pod is being monitored by the navigation and control system. All subsystems are supported by the lightweight carbon fiber structure. This unity creates an unparalleled power-to-weight ratio. We would like to thank our partners, friends and family for making this all possible. Get ready for ATLAS02 in 5, 4, 3, 2, 1.
Every team member put in their full dedication and their heart into this vehicle. Every little detail has been thought of and engineered to its limits. And everything finally came together to finally be able to reveal this vehicle to all of you. My name is Elja Ebbens, and I'm the Chief Engineer of the Delft Hyperloop team. And I will present you the technical details of our vehicle. The first thing you might notice is the aerodynamic shape. The aerodynamic shape which is caused by the shell that surrounds it. And with this shape, we can reduce the air resistance during a run. Because even in near vacuum, air resistance is still very much present, especially at the high speeds that we travel at. However, the aerodynamic performance is just one part of it. The real performance of this vehicle can be found under this aerodynamic shell. So, let's take a look. Arjan already mentioned that we designed this vehicle for a top speed within a short distance, which is why we designed it to be immensely powerful, yet remain lightweight. And this can be seen reflected back in 4 of its key design elements. First of all, it's compact. It's small in size, shy of 2 meters. And we do this because our design philosophy is that if you make it as small as possible, you make it as light as possible, which is just what we need. Secondly, we have a fully electric vehicle, and this allows us to quickly accelerate from standstill in a short period of time. Without any mechanical components, we can do this easier. During the run, ATLAS02 functions fully autonomous, and that means that it makes decisions and controls the pod without any user input. At these high speeds, human reaction time is just not fast enough anymore. We need to make split-second decisions, which is what the board computers can do. Furthermore, the vehicle is wheel-driven. It's propelled by 8 electric rotary motors. And by using electric rotary motors, we can propel efficiently, but most importantly, with very little mass. And this allows for a quick acceleration to our top speed. I will explain the pod's functionality and the properties by walking you through a final run, that one final run at this competition. So imagine it's the 21st of July, competition day. The whole team will have gathered in front of the SpaceX headquarters next to this vacuum tube. We transport this pod just in front of the tube. And from here on out, there's a couple of steps to be done. And we can split these steps up into different phases. First of all, we have the preparations phase, where you set the final configuration of the vehicle. Afterwards, the pump down phase, the acceleration phase, and the braking phase. The first thing that has to be done in the preparations phase is the suspension system. The suspension system clamps the drive wheels onto the track, and we need these to ensure traction. If you don't clamp hard enough, you will start to slip, and this is similar to riding your bike on an icy road. We exert this clamping force using a shock damper, and this shock damper acts as a spring, exerting the force, and as a damper, dampening out any vibrations we experience during a run. These 3 variables, the spring characteristics, damping characteristics, and the clamp force, are designed to be fully adjustable, because just before the run, we execute our final vehicle dynamics model, the model which simulates the movements of the vehicle during such a run. We optimize for these 3 suspension characteristics to maximize the traction, because every time a wheel hits a bump during high speeds, it goes into the air and loses traction for a split second. We have to minimize this. Having cranked out these numbers by the vehicle dynamics model, we can install them on the pod. We set the right configuration on the shock dampers and put them into the right correct orientation with the adjustable brackets, ensuring we have the exactly right clamp force. After the whole suspension is set, we can power on the vehicle. And we do this by a simple press of the button on top of the pod. All the low voltage electronics will be powered on, including the CPUs, which are the computers acting as the brain of our vehicle. With all the data it gathers, they can make split-second decisions, which is just what we need. Furthermore, the pod will automatically establish communication with the user outside of the tube. And the user can monitor the pod. It can see, for instance, the speeds of the drive wheels, which we can derive the speeds from. The battery health, by looking at the temperature and the voltage, ensuring healthy batteries before we commence a run. We have brake pressure to check whether we have enough storage on board to quickly brake to standstill at the end of a run. And for instance, the ambient temperature and pressure, knowing exactly at which conditions the pod runs at. The communication is established, and now we can pressurize the pneumatics. And the pneumatics is the high pressurized air system we use to activate the brakes. We pressurize the pneumatics with over 50 times the atmospheric pressure, allowing for compact and lightweight energy storage, which you can use to explosively brake to stand still. The pneumatics are pressurized, and that means it marks the end of this phase. We can proceed to the pump down phase. The pod will be transported to the start of the tube, and the SpaceX employees will close the 2 doors at both ends. The pump down will commence. But while the pressure in the tube is going down and we're reaching near vacuum, the tension in the team is building up. Because at this moment, everyone in the team knows that we're approaching the moment that we've worked an entire year for. At this moment, everything has to come together. There's no room for errors. There's no room for inaccuracies. We have to go. So we issue a final command. We launch, and the pod quickly surges forward, reaching towards the end of the tube. And we're in the next phase, the accelerating phase. And at the core of this acceleration, we have the powertrain. The powertrain consists of a battery pack, 2 motor controllers, 2 motors, and 2 drive wheel mechanisms. And one of this powertrain system can power as much to light up over 5,000 light bulbs all at the same time. And we do not use one of these systems, we use 4 identical systems on our pod. And this allows us to reach the high power output that we need. Having 4 identical systems gives us certain modularity in our design. And modularity has 2 key benefits. First of all, producibility. We have fewer unique parts, allowing for easier series production. And secondly, testability. If we test just one of these modules, we already have a good indication of the overall performance of the vehicle. But testing with just 1/4 of the power is much easier. These 4 modules together will generate the extreme power output. And this gives us an extremely high power to weight, which we can see once we compare it to a Formula 1 car. A Formula 1 car are one of the fastest and most technologically advanced cars in present day. The power to weight of our vehicle, however, is 3 times as high as a Formula 1 car, allowing us to quickly accelerate to our top speed. And to understand how it reaches this performance, we have to trace the power back to its source, the batteries. The batteries consist of lithium polymer cells, and we put these next to each other and layer them in an efficient manner, allowing for dense packaging. We build a custom structure around it for a very lightweight design. We laser weld each individual cell together to have a low resistance during discharge. And to meet the power requirements, we use a lot of these cells. Actually, we use almost 1,000 of these cells just on our pod. But having this high power demands a certain safety and monitoring. So we monitor each individual cell. And then we can see whether each cell is healthy, ensuring that the whole battery pack is healthy before we commence a run. During the acceleration, the batteries will discharge the current, and we can follow the current outside of the battery box towards the motor controllers. The motor controllers convert this power into the power that the motors can use. And while doing so, the motor controllers can accurately determine the speed of the motors, and therefore accurately control the speed of the entire vehicle. If we further on follow this current to the motors, we see that it converts the electrical power into mechanical power, allowing for a rotation of the axle inside. This axle is directly connected to the drive wheels. This allows for a direct drive mechanism. And using a direct drive mechanism, we can reduce the transmission loss, which you would else have with a gearbox, for instance. All these drive wheels will be powered, and they will do this synchronously, allowing us to quickly increase our speed for the high-speed phase. But before we reach that phase, we navigate. And of course, we can't use GPS because the pod is surrounded by a thick steel tube. We use the light strips inside of these tubes instead. Light strips are positioned every 30 meters along the length of the tube. With the diffuse sensors located on top of the pod, we can detect these light strips by detecting the reflected light touching and reflecting from these light strips. We count these, and then we can quickly determine our position. After we have counted 30 light strips, and being 900 meters onwards, we reach our most critical phase, the high-speed phase. And in this phase, the pod will face its harshest conditions. Because not only will the electronics reach the highest temperatures, the track irregularities that Arjan talked about will induce extremely high loads on the drive wheels. And this allows for a certain stability on our vehicle. We have the suspension system, which can stabilize the pod in vertical direction with the drive wheel mechanism and the horizontal direction with the lateral guidance mechanism, which is located inside the chassis. And this stability is extremely important, because at some points of the pod, the clearance between the track and the pod is less than 10 millimeters. 10 millimeters away from a catastrophic failure. But suspension will ensure that we never touch the track, even at the high speeds that we encounter. At the end of this phase, the wheels will reach their maximum rotational speed. And as Arjan mentioned, this poses a challenge, because no tire survives. They all get ripped off. So this is the reason why we don't use any tires on the wheels. We have a pure aluminum rim, because tires do not survive. At the end of the phase, we reach our top speed, where we aim to reach half the speed of sound. But we're now nearing the end of the tube, so we have to enter the next phase, the braking phase. But before we enter the braking phase, we have the chassis. And the chassis absorbs the loads that are going into the drive wheels due to these bumps. The chassis has been designed to do this as light as possible. And we do this by using a high-tech material. And the engineers in the public know what I'm talking about. It's carbon fiber. And we use carbon fiber and put them into the correct orientation, allowing for a strong and stiff structure, yet remain lightweight. The strength of the structure is not only determined by the material, but also by the geometry. So at some points, we locally heighten the structure, and this is called a stiffener. By including stiffeners, we can make the chassis stronger and stiffer, while not adding any unnecessary excess mass. But now we do reach our top speed, and we have to brake. And we brake by using the pneumatic system. The high-pressure gas in the pneumatic system is released to the calipers. And in these calipers, we house 16 pistons in total. The high-pressure air explosively presses onto these pistons, clamping the track in between the brake pads. And this generates a huge deceleration on our vehicle, bringing it to standstill. And I could tell you everything about this deceleration and show you graphs of how it performs, but I think it would be wise to compare it to something that everyone knows: cars. A Lamborghini, for instance, decelerates from 100 kilometers per hour to 0 kilometers per hour in just 2.3 seconds. And this is really fast for a car. It corresponds to a braking deceleration of 1.2 g. A Formula 1 car, which are the fastest and most technologically advanced cars in present day, can decelerate up to 6G. And this is comparable to the highest G forces you encounter in one of the most thrilling rides around the world. But ATLAS02 doesn't come close to this. No, ATLAS02 exceeds it. Because ATLAS02 decelerates with a peak deceleration of 20G. And this is insane if you think about it. To put it into perspective, if you were to drive your car at 100 kilometers per hour and you were to brake with 20G, you would be standing still in 2 meters. But we do this just because we want to win. And this is not how a real Hyperloop experience will be later on. But for the race, it's the perfect fit. The Hyperloop ATLAS02 will be standing still at the end of the braking phase. And this whole process that I mentioned, from the launch to top speed to standstill, just takes 10 seconds. 10 seconds where every part has to work perfectly in harmony together. But if everything does work perfectly in harmony together, we will celebrate. Because we aim to win the 2019 SpaceX Hyperloop Pod Competition. And then we bring the trophy to Delft.
However, we're not there yet. During the past few months, we have been working on designing ATLAS02. We have ordered all the materials that we needed, we produced all those parts, and put it together into one complete pod. But just building a pod is not sufficient if you want to win this competition. We need to make sure that it's safe and that it is reliable, and that it can output the performance we designed it for. And during the past few weeks and the past few months, we have been testing all our parts. We have been testing our subsystems. We partook in vacuum tests. We did free spin tests. But this year, there's something new. Because in close collaboration with our infrastructure partners, we have built a 400-meter long Hyperloop test track in Hilversum. And on this track, we will test our pod at high speeds, making sure that it can output the performance we need before we ship it over to California.
And that is what brings us to the last stage of our year. The team will travel to California, where we will do the last final adjustments to our vehicle, before we can finally convince the SpaceX engineers of the properties and capabilities of our pod. But doing this, we would like to thank you for listening to us, for helping us, and we would like to give you a little bit of insight of what life is like when we are there in LA. So we would like you to follow us online. Welkom allemaal bij Delft Hyperloop. We gaan weer terug. Welkom allemaal bij Delft Hyperloop. Mijn naam is Rinneke van Noort en ik ben teamcaptain.
Mijn naam is Asja Filmi en ik ben PR-manager.
De komende 2 maanden zullen we jullie door middel van dit soort kleine vlogs up-to-date houden en een uniek kijkje achter de schermen geven bij ons team. Vandaag zijn we op het kantoor waar heel veel mensen nog hard aan het werken zijn ter voorbereiding van onze presentatie die we binnenkort hebben.
staan nu in de Electrocave en hier zijn ook van allerlei mensen ook aan de slag om de laatste dingen van ons voertuig af te maken. Sounds difficult. Complicated.
Yeah, it is a little bit.
Joram, wat ben je aan het doen? Wat is dat?
Wat wil je? Wacht even. Je moet even van tevoren vragen wat je van me wil.
De komende tijd zullen we jullie meenemen in een uniek kijkje achter de schermen bij Delft Hyperloop. We zullen topics behandelen zoals team spirit, vertrek en aankomst alleen. Ja, logistiek, technische uitdagingen en alles wat we meemaken de komende maanden. Facebook, Twitter, LinkedIn, Instagram en YouTube. Stay tuned. Oh ja, trouwens, dit alles wordt mede mogelijk gemaakt door onze mediapartners. En je hebt nog kans om in te stappen in het mediaplan. Join us.
So today, we talk to you about what makes our vehicle so special. What are the properties of ATLAS02 that will allow us to win the competition? We talked about what we have gone through the past year, what challenges we have faced and how we have overcome them. But we've also talked about what our ideal future of transportation will be like. So if you were to ask us, how do you see yourself in 10 to 20 years? We don't know. But we hope to get there using the Hyperloop. Thank you. If you like to join us for the drinks afterwards,